Okay, so we are going to do some conservation of linear momentum practice problems. For this first video, we are going to look at the space shuttle, probably the greatest example of conservation of linear momentum. After the solid rocket boosters fall off of the space shuttle, and I'm sure you guys have all seen videos of them gracefully flying away from the space shuttle and then flipping over. It's beautiful. The space shuttle slows down, and this should set off your engineering spidey sense. It should be like, what the hell? And the reason it should set off your spidey sense is because the whole point of the shuttle is to go fast enough that once its engines turn off, it's falling fast enough that it keeps missing the Earth, right? It's in orbit, and so it's falling as fast as it's going forward, and it keeps missing the Earth and keeps going around and around and around. And the reason it slows down is that it's too heavy for its main engines to actually accelerate it, so it doesn't have enough thrust to actually accelerate. So my question to you is how long does it take for the shuttle to start speeding up again? So the mass of the shuttle, is 135,000 kilograms. The mass of propellant is 550,000 kilograms. M dot fuel is 1,400 kilograms per second. This is an incredible amount of fuel per second, right? This is just an enormous amount of fuel per second is burnt. The exit velocity of the fuel is 4,200 meters per second, and I have looked all this up, so these are all accurate numbers for the most part. And the velocity of the shuttle is roughly 1,000 meters per second at this point. So we're at Mach 3, because we're still in the atmosphere when this happens. So the question is at the moment that the space shuttle stops slowing down, is it accelerating? And the answer to that is no. It's not accelerating. Its acceleration is 0 at that moment, right? Its acceleration was negative, right? Because its velocity was going down, and then its velocity stops going down, and its velocity starts going up. So it's, by definition, its acceleration has to go from negative to positive, so it has to be 0 at that point right there. So great. The reason why that's important is that, and I've said this before, but I'm going to stress it now, is that we need an inertial reference frame in order to use conservation of linear momentum. There is a conservation of linear momentum for accelerating reference frames, but we don't teach you it. You can look it up. It's not a whole lot more complicated. You have to have a second coordinate system. You have to have a second coordinate system that is inertial and one that isn't inertial. But it's actually not that bad. We're not going to teach it to you here. But we do need an inertial reference frame in order to apply our plain old conservation of linear momentum. So yes, it's important that this is not accelerating. Its acceleration is 0 because that means it is an inertial reference frame for a moment. And that is the moment we are going to analyze. So we're relating forces to velocities and masses. What model do we use? Obviously conservation of linear momentum, where sum of the forces is equal to d dt integral over a control volume of rho v xyz dv plus integral over control surface of rho v xyz w dot n hat dA. Okay, so as always, we draw our control volume now. So I'm going to draw my control volume around the space shuttle like so. Ba-bum. I'm going to put my coordinate system with the space shuttle here, x, y, z. And then we pick a direction and write down our simplifying assumptions. So the direction I'm going to pick is obviously in the y direction. That's the direction I'm accelerating, and that's the direction that the fluid is leaving our control volume. So I'm going to pick the y direction. So the sum of our forces in the y direction is going to be equal to, we have a mass times acceleration that is acting on our mg, that is acting on our space shuttle, so a negative mg, which is equal to, at this point, a d dt, or the integral over our control volume of rho vy dv, plus integral over control surface of rho vy w dot n hat dA. So if we're going to write out our assumptions now, let's assume that we have uniform flow across our exit. That's not true, but we don't know the flow profile, so this gets us the best approximation that we can get, uniform flow. And we're also going to assume density is equal to a constant. So that just means that when the fluid is inside of our control volume, its density is a constant, and when it's crossing our control volume, the density is a constant across that surface. That's a reasonable assumption. Those don't have to be the same densities, it just but it does mean that either within the volume or at the surface, the density is a constant. Great. So what's wonderful about using our coordinate system, which is moving with our control volume, then, is that the mass within our mass of fluid that is within our control volume is actually moving at the same speed as our coordinate system, so its velocity is 0. So we don't have to deal with that nasty time derivative of a triple integral. So if we're using both uniform flow and density is equal to a constant, that means we can simplify our equation to negative mg is equal to rho times negative v exit. And the reason it's negative, because this is our vy right here, the reason it's negative is because it's going out and down, so it has a negative velocity, times our dot product. Now, our dot product is going to be, we've drawn our control volume perpendicular to our flow, so it is either going to be positive or negative 1, and because it's leaving, it's going to be positive 1, so this is going to be v exit. And then we multiply by a exit. Now we'll get to this, but I don't actually know a exit, right? But I do know that rho times v exit times a exit is m dot for our fuel, m dot fuel, because all the fuel that's burnt has to leave. So we can rewrite this as negative v exit, which is 4,200 meters per second, times our m dot, which is 1424 kilograms per second. And we find out that our m total, then, this is mass of our fuel and rocket, is equal to that divided by 9.8 meters per second. So we take the g over to the other side. And our m total then, if we cancel out our negatives here, our m total is equal to, I love this, 6.1 times 10 to the 5th kilograms. It's a lot. It's a lot of fuel, right? So our m total then, also, m total, we can write is equal to m shuttle, that doesn't change, plus m dot fuel minus m dot fuel times T plus m propellant. Great, so if we know m total, we know m shuttle, we know m propellant that it starts with, and we know m dot fuel, we can solve for T. And what we end up getting is that if we plug everything in, that T is equal to 52 seconds. What? Yes, I did not mean to not have an H in there, but there's no H, so I think that's appropriate. That is a long time. It only takes about, two and a half minutes to get into space, to actually get into orbit. So maybe, actually, I think it's about 3 minutes. So we're spending almost a third of that time not accelerating. That's insane. And if you want, I'm not going to do it now in a video because, well, maybe I can. Yeah. Feel free to stop now if you want listening to this. You can move on to the next video, which is going to be a different problem. But I'm going to explain why the space shuttle slows down for 52 seconds. And it's an incredible reason. These first question you have to ask yourself is, these solid rocket boosters, what limits how long they can burn for? So those of you that are in the rocket club will probably answer this quickly. But it turns out that the duration that a solid rocket booster burns for is given by the thickness of the lining of the fuel in the rocket. So a solid rocket booster is literally just a tube where the tube is lined with solid propellant. They light it, the flame travels up the middle of the rocket and burns from the inside out, right? Not from the bottom up, but from the inside out. You don't want it to burn from the bottom up because that hot fuel will then melt your rocket. You want it to the hot exhaust to ignite more fuel. So it burns from the inside out. So the wider your rocket, the longer it will burn, right? If you want more thrust, you have to make the rocket taller. And the rocket actually comes in segments. So the height is just a limit of how many segments you want to stack on top of each other. So the real problem is how wide of a rocket can you ship? And so if you're trying to ship a wide rocket, where's the worst place possible to build one of these rockets? I want you to stop and think for a moment. It's got to be built in the United States. This was designed in the 1960s. Yeah, 1960s. I can't remember when the first one flew, but it was right around 1969. And oh no, it was designed in the 70s. Either way, it required a massive appropriation from Congress, which means that it had to be built in the United States because that money had to go to some state. So, built in the United States, where is the worst place in the United States? And you might say, oh, well, if they're leaving in Florida, the West Coast. But no, West Coast is actually a good place to build these because you could put them on a barge and ship it through the Panama Canal. Done, right? No, what's worse than there? And you might say, well, what about the middle of the country, like St. Louis? No. You could ship it down the Mississippi for the most part. Those rivers are really, really quite deep and wide. No, the worst place to build this would be in the middle of the Rocky Mountains because there's only way to get stuff out of there is by rail. And the rail cars go through the mountains. So they're limited by the diameter of the mountain, or diameter of the tunnels that they cut through the mountains like 100... When did they do this? At the 1800s, so over 150 years ago, right? So they're limited by these tunnels, right? And these tunnels were only wide enough to allow a normal-sized rail car to go through, and that size of that rail car was set by the size of wagons that people used, right? Going out west, and so there's this fascinating propagation of decisions where the choice of a certain wagon gauge, right, which has stayed relatively stable throughout time because these wagons make these ruts in the ground or in roads, and if you make your wagon wheels a little bit wider, a little bit narrower, you'll be stuck in one rut and not the other, and you'll break a wheel or an axle, which from Oregon Trail we all know is a terrible thing. So throughout time, these have been relatively stable, even so much so that you can trace from the Roman Empire this gauge of wagon width all the way back to there. And it actually ends up being the width that comfortably holds 2 horses, right? So the width of 2 horses in this weird chain of events limits the acceleration of the space shuttle for almost a whole minute. And our acceleration, or not our acceleration, our calculation, by the way, is pretty accurate. I think it ends up being 4 40 something seconds or something like that. Like it's a relatively accurate calculation given that we looked up all these values on Wikipedia. So that's fun, right? We literally threw our best scientists at this problem, and because the only place that could manufacture this big of a solid rocket booster was in Utah. Again, why Utah? Um, it literally has to slow down for a period of time.